Thanks for joining the session today. I'm going to talk a little bit about software rasterization of point clouds and how we can be faster than the hardware pipeline using it. So the problem that we're trying to tackle here is that when you're doing some laser scanning or aerial LiDAR scanning, you end up with point clouds with a lot of points, so millions to billions of points. And here, for example, we have data sets with 4 million points, 500 million points, 1 billion points, and 640 billion points. And we'd not like to be able to render these kinds of points in real time without pre-processing. And at least for anything that fits on the GPU, we can make this work with software rasterization. For anything larger than that, we will still need some kind of level of detail structures. So let's take a look at the related work here. First of all, if you're trying to do fast rasterization of points, you might want to take a look at native point primitives like GL points, point list, and so on in OpenGL, DirectX, and Vulkan. In DirectX, it will produce pixel-sized points, and in OpenGL and Vulkan, you can even create sized quads here. The problem with those is that they are largely built on top of the triangle-oriented hardware and rendering pipeline. And Günther et al., they found out that using software rasterization, you can actually beat GL points by an order of magnitude. And the approach they were using is to use spin lock to atomically update pixels color and the depth buffer. And once a thread updated the depth and color buffer, it then unlocks the pixel again for another thread or another point. Mars et al., they used atomic min-max operations to reproject depth buffers to multiple views. And they were using 32-bit atomic min or max operations. And with 32-bit, this was enough for depth values, but it wasn't enough to atomically update the depth and the color buffer. In our previous work about rendering point clouds with compute shaders and vertex order optimization, we then used 64-bit atomics to simultaneously update an interleaf depth and the color buffer. So we just encode both the depth and the color value into a single 64-bit integer, and then use atomic min to find the point of the smallest depth value. And of course, there's also Nanite related work. Nanite, they found out that for very small triangles, it's actually faster to use software rasterization using 64-bit atomic min-max operations to find the triangle with the smallest depth. And what they do is they encode the depth and the triangle ID into a 64-bit integer, and then the 64-bit atomics to find the closest fragment. So the contributions of this paper, so our paper directly builds on the previous paper about rendering point clouds with compute shaders. And previously, what we've done is we rasterized points with the 64-bit atomic min operations. And we also did some improvements like avoiding contentions with subgroups. So if we have 10,000 GPU threads that try to simultaneously update one single pixel, that leads to some contention that seriously hurts performance. And with subgroups, you could merge multiple points in a warp into one single atomic update. And we were also checking some various different vertex orders and found that, unsurprisingly, Morton order performs very well, at least for compute shaders or software rasterization, but it worked terrible for GL points. So what you could do, for example, is to do sort by Morton order and then do some kind of shuffling so that you have good locality from Morton order, but not too much locality that would hurt performance of GL points. The problem with that is that we still have bottlenecks in the scheduling of the threads and especially with the bandwidth usage. So the new contributions of this paper here is that we are now using a batched approach. So we group multiple points to a batch. And this allows us to efficiently do things like frustum culling, LOD rendering, and also importantly, adaptive coordinate precision, which significantly reduces the bandwidth that we need. So the generation of the batches is actually pretty stupid. We simply group 10,000 consecutive points in memory into a batch and compute a bounding box of that. And this works fine in most cases, so for many data sets that you find in practice. And if it doesn't work, you can simply sort by Morton order and it will work fine. So to the right here, You can see a small point cloud with 1,000,000 points, and at the bottom here, what this looks like if you color this individual batches here. So in previous work, we were spawning one thread for each point, and this isn't very efficient scaling-wise. So what we're doing now is we spawn one workgroup for one batch. So one workgroup has 128 threads, one batch about 10,000 points. And the first thing a workgroup does is it does frosting culling for this batch that it processes. And yeah, if the batch is not visible, it aborts right away. This approach is now also nicely compatible with LOD rendering, and the workgroup can also check if this level of detail node should be called. And then the workgroup computes the required coordinate precision for this batch, and then each thread of this workgroup proceeds to render about 80 points. So it loops through 80 points instead of rendering one single point per thread. So the adaptive coordinate precision, this is one thing that significantly improves the performance here, because the previous work was limited by memory bandwidth usage. So we were able to render up to 50 billion points per second, but with 16 bytes per point, that was a memory bandwidth usage of 800 gigabytes per second. And this already hits almost the limits of the highest-end graphics cards. So what we're proposing to do instead is to do some kind of adaptive precision, where instead of storing the points as floating point coordinates that need 32-bit per axis, instead we store a point in fixed precision coordinates and use 10 bits per axis. So we need about a third of the memory bandwidth now for the coordinates. And 10 bits, that is sufficient to encode about 1,000 different coordinate values. So assuming that a batch is smaller than 500 pixels, 1,000 different values per axis is more than enough to represent this with high fidelity. If your batch is much larger than that, or larger than 500 pixels, we can simply on demand load additional bits. So by default, we load these 10 bits here from this low precision buffer. And if we need 20 bits, we still load this 10 bits from this low precision buffer, but we also load another 10 bits from this medium precision buffer. And by putting them together, we get a 20-bit coordinate. In any case, if you look at this image to the right here, you can see all these individual batches colored differently. And you'll find that any of these batches, all of these batches here, are smaller than 500 pixels. So only when you zoom in very closely to something, you will end up with some batches that actually need 20 bits, and most batches in a scene will always need 10 bits, even in close-up views. And if you look at the bottom right here at this individual batch here, you can see that the batch is not optimally compact, because we're simply grouping 10,000 consecutive points in memory into a batch. And you get some jumps from the Morton code order here. But that is usually perfectly fine. So you have some batches with small jumps, and there are very, very few batches with large jumps. And if you have a couple of batches with large jumps, you simply render them with 20 bits precision. So another thing that's now possible efficiently is level of detail rendering together with the layered point cloud structure. So a layered point cloud is a spatial hierarchical structure that originally uses binary tree. We're using an octree here. And each node of this hierarchical structure has a subsample of the full point cloud. So when we're looking at this root node here, we get a very coarse subsample of the whole point cloud. And since it's an octree, we have up to 8 children here. And each of these children, they have some additional points that we can render to improve the detail. And in order to make this level of detail structure work with our software rasterizer, we just need to do 2 changes to the pipeline. So first of all, we simply treat each level of detail node here as a batch, and a batch with a variable amount of points. So previously, I said that each batch has about 10,000 points. Now it's closer to about 1,000 to 50,000 points. Doesn't really matter. And the other change that we do is we discard small nodes, so nodes that are smaller than about 100 pixels. Because these octree nodes, they contain more details than we really actually need, so we discard them to save some performance. In the paper, you will also find some further optimizations that you can look up, like, for example, visibility buffer. We use a visibility buffer now, where instead of rendering the colors, we render the point indices and resolve the color afterwards. We also use some prefetching, where when each thread loops for all its points, and instead of loading one point and then render it, loading another point and then render it, we load 4 points at once and then render these 4 points, and then we load another 4 points and then render these 4 points. And this is a surprisingly big performance improvement of about 30%. Also, if you're doing virtual reality rendering, you can render the periphery at a lower amount of detail, because geometric details in the periphery, they are not as visible as in the center. So regarding the results, this method, the main intention here was to have a fast brute force rendering performance. And we were able to render 1 billion points in about 6.4 milliseconds on an RTX 3090. And of those 1 billion points, about 910 million points were actually processed, and 90 million were frustum called. So about 10% were frustum called in this viewpoint here. What this means is that 140 billion points per second were processed and rendered. And if you calculate this in terms of how many we can render in 60 frames per second, we end up with a value about 2.3 billion points that we can render at 60 frames per second. We also had a high GPU utilization with that. So this speed of light that you can compute with the NVIDIA profiler, for compute it was about 79%, and for memory 91% with the prefetch optimization. So if you don't do the prefetching, this memory utilization was much, much lower, and also the performance accordingly lower. So we also tried applying this to virtual reality rendering, and this data set here, it has about 528 million points. And for virtual reality, we used a level of detail rendering because we needed extra performance here. With the level of detail structure, we ended up rendering 21 million points here and still got a good quality. And to also have some kind of super sampling, anti-aliasing, we rendered into 2 frame buffers with 6.8 million pixels each. And all of that took about 8.3 milliseconds. So well below the amount of time that we need to render at 90 frames per second in virtual reality. So here's an example of what this can look like and when rendered. And here you can see what the individual chunks look like. So these are the chunks that you get by grouping 10,000 consecutive points in memory into one batch when the point cloud is sorted by Morton order. So wherever there's a high density, you have smaller chunks, and where there's a low density of points, you have larger chunks. When you're using the level of detail structure, you end up with chunks like this here. They're very regular because we're using an octave structure, and the more detailed, the finer, the smaller chunks, they're now discarded at runtime because batches that are smaller than 100 pixels, they have detail that we don't need anymore, or that we don't need as much anymore. So, of course, there are also some limitations, like the quality-wise. We were aiming for rendering as many points as fast as possible to compete with the GL points performance and to make it about 10 to 100 times faster. But we don't compete with surface or splat rendering, which targets high-quality rendering. However, you can still use some blending approaches where you blend together overlapping points. So if you look at the left image here, this is what you get with the normal point rasterization, just taking the closest point. This is also what you get when using GL points. And to the right here, this is what you get by blending overlapping points together. And it reduces the performance by a factor about 3. But this is also used for virtual reality rendering because you need that extra quality. So high quality together with level of detail rendering, then you will still end up with enough performance. So other limitations is, yeah, we are rendering pixel-sized points. In this future work, we'd like to take a look at splat rasterization, so softer rasterization of splats, and try to see if we can also make this faster than current approaches that use either GL points or some oriented triangles or quads. We are also using right now still 16 byte per point. So we'd like to take a look at compression algorithms that can be decoded fast at runtime. And we're hoping that maybe there's something that could compress points down to 1 byte or 2 bytes per point so that we could fit up to 10 billion points on a GPU. Also, color filtering is quite expensive right now, but if you're using LOD structures, you could do color filtering in lower levels of detail. So there's also some optimizations that could be done here to make it faster and look nicer. So yeah, I'll skip this here and go straight to the practical uses of our application. So our intention, so our motivation for this thing was to be able to look at large amount of LiDAR data sets as quickly as possible without having to spend time for pre-processing like downsampling or generating LOD structures. So here we can simply take all of these LAS files, drag and drop them in here and look at them right away. So this is about 100 million points right now. We can also take the remaining LAS files here, rendered in real time while it's still being loaded without generating any LOD structure. And we end up with 570 million points here, rendered in real time. And in this case, with the high quality splatting, so blending of overlapping points. Also, another use case that we didn't anticipate, but which was pretty nice to see is this ADOP paper here, where they use fast software rasterization of points as a component of a neural novel view synthesis pipeline. So they're first rasterizing these points quickly, and then they're using a neural renderer to improve the results and to reconstruct a proper image out of that. And yeah, this paper will be shown at SIGGRAPH 2022, so I'm looking forward to seeing that in person as well. And yeah, thank you for attention. If you want to take a look at the code, feel free to check out this GitHub repository.
Thank you, Markus, for a fantastic presentation. We've got time for questions if people want to write them on the question board. In the meantime, since we haven't got any there, I was just wondering about the Morton order. I can see that it's a good one-size-fits-all approach, but I was just wondering if can you also produce some other orderings that would be sort of better for particular view directions? So making it narrow, I suppose, narrow in the direction you're viewing.
Yeah, I think so, yes. Maybe you could even generate batches with kind of the same data, but better for a specific viewpoint by having some duplicate data specific for a viewpoint. You could probably also generate more compact batches by using some kind of binning approach instead of Morton order. And with this binning approach, the difference is that you'd probably end up with batches with different sizes and not always 10,000 points, which is fine because that's the same thing that we're already also doing with level of detail rendering. So as long as it's in the order of about 1,000 to 50,000 points, it's not a problem. And if it's larger than that, you could still process the batches to make them finer grained or split them to avoid too many jumps, stuff like that, yeah.
Okay. Oh, we have a question. How would your approach scale to different primitives, such as line segments? And what would be the challenges in this space?
Oh, that's a very good question. I actually want to try line segments at some point as well. I think it might have some, or it might have definitely potential for that, because I guess lines are also probably built on the triangle hardware rasterization pipeline. And in many cases, if you have a lot of lines, like there was a paper at Eurographics, this Fiblet rendering, you have billions of lines, but you only have a couple of million of pixels. So most of these lines, they will be very small, maybe even pixel sized or sub-pixel sized. And in this case, this point rendering might actually speed up the line rendering. What could be difficult is if you have larger lines. So Not yet sure how to approach that. Maybe even with an approach like Nanite, where larger lines still get passed to the hardware rendering pipeline, but smaller lines get directly rasterized in software.
Okay. Maybe we can just squeeze one more question. Could the blending of different points be replaced by a stochastic approach and temporal recon?
Yes. So this ADOP paper, for example, they do already use a stochastic approach, not for blending, but for removing points to save some performance. But yeah, I also don't see any reason why a stochastic approach wouldn't work. Yeah, but I can't think of it right now from the top of my head.
Okay. Well, I think we're probably out of time for questions. I think we should just thank our speaker one more time. And we should move on to the next paper.